Presentation of the work entitled Blockchain-Based Machine-to-Machine Communication in the Industry 4.0 Applied at the Industrial Mining Environment at SBESC 2020. Currently, millions of devices are appearing that are able to process information and interact with the environment in an intelligent and independent way. With the popularization of these devices, it was necessary to develop new communication protocols designed to deal with their limitations. Most implementations of communication protocols use decentralized cloud-based model that requires a trusted intermediary for communication between devices. With the intention of establishing a decentralized point-to-point network and without the need for a reliable intermediary, several works are introducing blockchain and the industrial environment. The main benefits pointed out in these works are secure, traceable, and independent communication. Despite these recent developments, the works that apply blockchain in the industrial environments disregard the following characteristics: strict real-time requirements, industrial devices without support for Internet-based communication, lack of developments and practical assessments in real environments. In addition, all existing works need a cloud infrastructure to deploy the blockchain network. The cloud infrastructure offers great hardware resources, but increases the distance between the devices and the blockchain network, increasing the communication delay. Faced with these problems, this work proposes a decentralized communication architecture in which the blockchain network is deployed directly on Internet of Things devices, eliminating the delay generated with cloud devices. The blockchain network is a decentralized point-to-point network with no point of failure, whose transactions cannot be deleted or altered. Blockchain is highly scalable and all transactions are encrypted, making them secure and auditable. At the heart of this technology, there are consensus algorithms, which are protocols for achieving reliability in a network of several untrusted nodes. Smart contracts are computer protocols designed to facilitate, verify, or enforce digitally the negotiation or execution of a contract. An overview of the architecture is illustrated in the following figure. Through smart contracts, the blockchain network acts as a communication intermediary between synchronous and asynchronous systems. In this context, an evolution from industrial applications to a decentralized approach is defined as decentralized applications. Decentralized applications monitor, control, and execute actions at critical levels of process control and fill the devices with the blockchain network. Decentralized applications can request queries or transactions for the blockchain network. The queries do not generate change in state, so REST API receives this information directly from the validator. For state changes, it is necessary to execute the smart contract for address analysis and storage status. In order to show the viability of the architecture, an iron ore conveyor belt slot identification system was developed. To identify the belt tier, two CypedMax boards were used, which were coupled to two other Raspberry Pi 4 boards that represent the nodes of the blockchain network. In addition to the two Internet of Things nodes, a workstation was also used to represent the monitor device, which triggers the interruption of the conveyor belt. We assess communication delays against the strict real-time restrictions that a conveyor belt system imposes on decision-making. Two scenarios are evaluated: a real case in which only one transaction requires stopping the belt, and a systemic stress in which 1,000 transactions are submitted to the blockchain network. Convergence time required for Internet of Things devices to agree that there is a break in the conveyor belt is evaluated. This metric consists of the delay to send, process, and consult the transaction. The following table shows the results of the convergence time. There is a low time of convergence and variation for the scenario of nearby Internet of Things devices, while there is a high time of convergence and variation for the scenario of distant Internet of Things devices. This time difference occurs mainly because there is an additional time of 16 seconds that represents the delay for the conveyor belt to travel with the tier at a distance of 80 meters that separates the two Internet of Things devices. Although the transaction latency has a short average execution time, in the industrial scenario, the standard deviation of this operation can make the system unsafe. The high variability of the data makes the proposed architecture unstable, especially in the scenario of systemic stress. Each time an operation is performed, it will result in a high degree of unpredictability for the completion of the requested operation. Time variations in convergence times can affect compliance with the deadlines within which specific tasks must be completed. For the real case, the average execution time and standard deviation of blockchain operations can guarantee a time frame of around 100 milliseconds. These results are important for the application of this proposal on the conveyor belt and also in several other industrial case studies that require few interactions with the blockchain network. Therefore, the application of blockchain technologies for communication in time-sensitive Internet of Things applications has its operation affected mainly by the amount of interactions to be carried out on the blockchain network. Currently, several blockchain approaches to Internet of Things define the blockchain network above the Internet of Things device layer. This is because most industrial devices are time-sensitive. Faced with this challenge, this work sought to incorporate and evaluate in practice the blockchain network deployed directly on an Internet of Things device. Despite the limitations of Internet of Things devices, the approach presented in this work presents a reduction of hardware and software that reduces the latency of communication. However, Internet of Things applications acquire new features that can negatively influence the energy consumption of Internet of Things devices deployed over long periods of time. Communication latency and variation are very sensitive in industrial systems that are synchronous in real time. Thus, current blockchain platforms for communication are not suitable for all environments, requiring the design and development of technologies that do not compromise the rigid requirements of industrial systems. In order to reduce latency time, there is currently an effort in which the blockchain architecture is extended to a more sophisticated architecture. This approach leads to parallel transactions, which reduces transaction latency, allowing communication closer to real-time requirements. However, such an approach does not allow for the execution of smart contracts. Finally, the evaluated case study thus has no mobility. However, mobility is a permanent feature in other industrial devices. With Internet of Things devices in constant motion, communication with the blockchain network will face high dynamism and large amounts of connectivity failures. This scenario will contribute to reducing communication opportunities between Internet of Things devices and the blockchain network.